It's my pleasure to introduce Dirk Werle. He's a geographer, and his company is Erde Environmental Research. And I think just before the break, you were explaining Erde as earth and water. Earth and water. Then it's a combination of...
It's a combination of old Germanic words. Au is the water part, A-E, and Erde is earth, as in Erde.
Right. So Dirk has done quite a bit of work with satellite radar, and so he's kindly given his time to us today to talk about satellite radar applications for the coast. So Dirk, it's all yours.
Thank you. I was a little bit apprehensive about the acronym SAR, because in many people's minds it also stands for search and rescue. So that's why you find in your schedule this morning the slight deviation or specification that I will mainly talk about satellite radar this morning. I will take a very broad definition of coastal, but I take a more specific definition on what kind of radars I want to talk about this morning, and I've narrowed it down to satellite imaging radar. Now, the coastal part, as this radar sat mosaic of all of Canada shows, that we have plenty of coast to deal with. And I would like to use a number of examples from our various coasts to illustrate the coastal applications of radar to you in the next 30 minutes. And I've tried to put it into four sections. The first one is an outline of the SAR technology and history. The second will be on actual radar satellite systems. The third, the main chapter, will be on applications, and I'll round it off with an outlook in the fourth section. Radar, imaging radar, especially from satellites, we tend to think of it as being the era of CSAT in the 1978 era as the first radar satellite. But as we learned just a couple of years ago, that was not the case. The American military was way ahead of us, and they launched the first radar satellite experiment in December of 1964. So there was a satellite up there for 4 days only, but it provided these image strips over the United States, including one that I will focus on here on the California coast, which intrigued the oceanographers, or those who had access to the to these images quite a bit, because you could see wind and waves on these radar images. And that informed, I think, a number of people who were responsible for the development of the American CSAT satellite that was then launched as a civilian satellite in 1978. But have a close look at these wind and wave features that were outlined here, later picked up in much more clarity by the equivalent of the civilian satellite, in this case the Canadian RadarSat satellite, much later in 2001, showing clearly the wave patterns here at Point Reyes, and then the refraction of the waves here. CSAT followed in 1978, so that was a decade and a half later, and the CSAT satellite was really a radar satellite. It had an imaging radar, it had an altimeter, and it had a scatterometer as the main instruments. And as far as the imaging radar is concerned, that we'll be talking about this morning, this here was pretty much the gold standard for future satellites. An image swath of around 100 kilometer, and as every imaging radar, you had to look sideways, and for picking up features on the ocean, look angle had to be fairly steep. That varied later on, but this essentially was the imaging geometry, and still is the imaging geometry of all the radars that we are working with from satellite altitude. The first images from CSAT were quite amazing, very similar here to the point race images just a little further up the coast. The outflow of the Columbia River in Washington, Oregon, with the freshwater lens here and the boundary over there. This imagery was processed optically, not in digital terms, and it looks a little fuzzy. Enter a Canadian company, McDonald Detweiler. They were the very first. They beat even the Americans to processing CSAT data in 1978 by producing a digital SAR processor. And this is the kind of images that a digital SAR processor could produce. Again, a CSAT image in 1978. Images that we can now, with even better digital processing capacity, improve on. And just have a look at the detail that these images produced at a resolution of around 30 meters. Many features on the land side, many features on the ocean side as well. Internal waves, gravity waves, surfactant and so forth was all in evidence here. There was another thing that CSAT produced, but that was not in evidence at all. And I'm referring here to the measurement of the altimeter, which was able to sense differences in sea level height at very, very minute detail, on the order of centimeters really. And by happenstance, a grad student came up with the idea of fuse together all these sea surface height measurements at the time, and lo and behold, the map looked very much like the seafloor map that was known, except that he covered a few more seamounts that hadn't been discovered at all at the time. Yet this global radar altimeter map that CSAT produced in 1978, and that was exploited by a grad student, gave us this iconic map of the global ocean seafloor, although in reality it was just the gravity that produced these different heights, but they mimicked the seafloor underneath. Just as an example, that radar is a technology that is not very intuitive to us for our eyes, but that provides us with very, very exciting other types of information. For instance, because of the sensitivity of radar to motion, because of the sensitivity of radar to roughness and so forth, it can provide us with very exciting information. At the core of that radar technology are these phased array antennas of the satellites with these individual transmit-receive modules mounted on them. Transmit-receive means the radar signal is transmitted through these modules, and the return, the echo, is received by the same an antenna in terms of the signal strength that's returned, and in terms also of the signal phase, a very important point that I will come to in a minute. But these antennas are really the core of modern imaging radar technology to date, and they allow us to really make some very, very detailed measurements on the millimeter scale. That is to say, half the wavelength of the radar that's being used. So if you're using a radar with 5 centimeter wavelength, you can actually make measurements on the order of half the wavelength, that is to say, up to a detail of 2.5 centimeters. And that comes in quite handily for a number of applications that I will show later on. For instance, subsiding ground as a result of an earthquake or other types of subsidence that can be measured with satellite radar through a process that's called interferometry. Here's an example of how interferometry is used in the volcanic islands of Hawaii, taking measurements over a period of several months. You can then see the deformation of the magma chamber here in the period of 2003 to 2005, how the caldera actually subsides or expands when new magma is coming up. And all of that is at a scale, in this here, of 2.83 centimeters, half the wavelength of the radar that was employed. So all these fringes here are changes of 2.5 centimeter or almost 3 centimeter increments. Very, very detailed stuff. For the same thing for earthquakes, displacement of earthquakes, of terrain as a result of earthquakes is illustrated here for the recent example in Chile, just this past September. So these fringes indicate the amount of earth displacement as a result of the earthquake. And the nearer you get to the epicenter, the closer gets the spacing of these fringes. So you can actually image the extent of an earthquake with a synthetic aperture radar quite nicely. The other thing that we exploit in analyzing radar data is the polarization of the radar signal, which can be in a horizontal way like this, or in a vertical way like this as the signal is propagated. And it can be transmitted in that way, or received in that way, or received in a what's called cross-polarization way. That used to be the standard procedure until some people came up with much, much more intricate and accurate measurements of polarimetric radar transmissions and return that use not only the vertical transmission or receive or the horizontal ones here, but they use the entire polarimetric propagation as the radar signal goes from the antenna down to the Earth, interacts with the Earth, and the echo is then sent back. And all the measurements around this elliptical polarized signal is being used to analyze targets on the ground. And that makes it a very, very powerful tool, in fact. Another piece of information is exploited for change detection. And again, it's at the signal level, at this very, very minute level. I have an example here of a sports field that's being mowed or is in the process of being mowed. Usually if we have change detection, we take two images and compare the two, which we can do, and we would get the result, yeah, there's something here that's different from here. Here we get more return than we get here and here and here. So that would be the usual change detection that we do. But if we take into consideration also the way the radar signal at the centimeter length interacts with the grass surface here, we will find through coherent change detection that the image actually